Well, it's surprising to me that people started with any language as opposed to getting away from characters and letters and didn't normalize on something that would be common to all languages, like a concept or something like that. Like the fact that you'd have to do it totally different for a German letter or a Chinese character.
Yeah.
It just seems inefficient and seems like we could have thought about that a little bit differently at the very beginning.
Well, I'm sure that they did, right? But the problem is, if you're English, if you're an American, for example, and you grew up in the US, I mean, what are the chances you know Hindi or Mandarin or German
Yeah,
or
you're not going to
Russian,
know that. Yeah, you go with what you
right?
know.
Right.
Welcome to Practical AI, everybody. My name is Jeff. I'm here with Peter Lynn. Practical AI is sponsored by Pocket AI. Pocket AI is a tool you can use to edit the weights of your model. With Pocket AI, you can prune over 60% of the weights in your model while increasing accuracy. Peter, today we wanted to talk about tokens. And in particular, there is a new advancement in the token space, and it's resulted in a new acronym that I learned this week called LCMs. So while you are explaining that to us, I'm going to bring up a video, a YouTube, and you can just tell us what LCMs are.
Yeah. LCM stands for Large Concept Model. And this goes back to a well-known problem or limitation with tokens. And if you go back to kind of Andrej Karpathy's videos about GPT and how tokens work, one of his quotes that he's said over the years and people have quoted him is, most of the problems that you find with LLMs is because of the tokens, meaning that if you don't have the right tokens, you can't train the model to do what you want it to do.
While you're doing that, I'll show one example here on the screen that they talk about, and this is a common one that tokenization screws up. How many R's are in strawberry? And the answer typically that they give back is 2, because the token strawberry is 1 token, right? It's not 2, so it's not counting properly or something like that.
Yep. Yeah. And so, for example, when Llama released a new version this year, they increased the token count by quite a bit, right? And this is to address that problem that's well understood, which is the tokens really is the foundation, because that determines how granular your model can be. So if you got, let's say, a model with only 100,000 tokens, that's probably not enough. If you got 1 million tokens, that might be enough for some things, but probably not enough for a general intelligence. And so as a result, really, that forces you to kind of train new versions of models with different tokening approaches. And so the large concept model does away with static tokens and tries to kind of add a separate layer where you determine what dynamic token you want. And that is, it's more like a patch. They're calling it a patch, meaning that it can be a dynamic mapping between words and tokens. And as it trains, it can actually modify and change that.
Okay, so I think the first question then is, will tokens disappear altogether? Like, are they going away, or is this just a version of token? You use the word dynamic versus static. Is
Yeah.
that conceptual in knowledge, or in example, or is it actual? Is it actually actual tokens that are just dynamic now?
So really kind of this goes back to why and how transformers were invented in the first place. Um, Originally, when people started analyzing text, they kind of use bag of words or bag of characters to try to group characters together. And then that was kind of one of the early methods for taking a sentence, chopping it up into small chunks, and then being able to kind of use that and train models. The main limitation is that that's dependent on the data you give it, right? So if you only gave it Shakespeare, it's only going to generate tokens based on Shakespeare. When you go and ask questions for French or German or Russian, well, one, Russian has sort of characters that aren't in English. So then when you ask it and you type in Russian, it's going to be like, I don't know what these characters mean.
So the token,
And
the transformer is limited to how the tokens are set up and the
yep,
number of tokens and how they're defined. So there's baked in limitations with
yep,
tokenization.
yep, yeah. And so, but the reason why we went that approach early on is because that's the easiest way to do it, because no one knows the optimal way to map language to tokens. And this new approach, concept model, basically we're training the model to figure out, hey, what is the optimal way to break up characters and map them to tokens? So in this case, they're trying to map it closer to concepts.
Okay,
and
so
becomes
if maybe this is putting you on the spot too much, but if tokenization is more similar to like a stenographer, where we're basically
yep.
you're going through the lens of the stenography, machine essentially to create sentences and stuff like that. What is this concept approach similar to? Is it relatable to anything?
So this goes back to kind of classic AI research, where originally when kind of AI first started with trying to build machine learning, one idea was using inference rules or production rules, which you would define concepts and you would define those concepts in such a way that a machine could use it. So one of the most popular projects for that is called OpenPsych. That's been around for at least 30 years. I mean, it's longer than that. OpenPsych's been around since I think 1970s, and the military uses it and other businesses use it. Um, and before neural networks got popular, Google actually built their own kind of knowledge database using RDF, which is the W3C kind of data format to encode ontologies and concepts. And so this is kind of an old thing, but the limitation with doing it manually is it's not optimal, and it's really labor intensive. It takes decades to build these things.
These contact or concept models, essentially.
Right. So it's really a concept database. So like OpenPsych is a concept database,
Okay.
basically. It's got definitions for things like table, chair, bird, mammal, fork, spoon, knife, right? So it's got all these concepts and it's got definitions of those. Um, and because humans are humans, our definition for fork could be a fork with 2, 3, or 4,
Yeah.
right, tips. Or like knives could be any number of shapes, or
Yeah.
chairs could be any number of things. And so we have these fuzzy definitions of what things are. And so how do you define a concept, right? It's not straightforward.
Right. And then it changes from person to person and
Yeah.
but what this reminds me of is kind of one of the topics or discussions we've had over time here, and that is that in order for AI to advance, it has to go back and use some classic ancient tools or ancient methods in order to advance, right? It can't just ignore the past. And here's an example of essentially a database, if you will, of concepts.
Yeah.
And and that's something that we've been sort of a proponent of for quite a while.
Yeah. Yeah. And actually, I mean, that's kind of the whole joint embedded kind of approach that Yann LeCun and Meta is going after, the triple and V-triple approach, where they're trying to map things more closely to concepts, because in theory, that should get you better way to map concepts to logic, and then be able to more easily prove that the logic and reasoning in these models is correct.
Now, one of the things, adjectives you used earlier was dynamic. How dynamic is this concept database? Is it ever changing, or is it a manual process of updating it and changing the concepts as the definitions change, or as you get into a different culture or whatever, where the concept might be a little different?
Great question. So the answer is that no one actually knows. So the LCM basically looks at the data and then it makes a guess at what is a reasonable mapping between a concept and some tokens or some characters in this case. But as it trains, it might go, oh, actually, instead of mapping header, I should map it to head and ER, because there's a lot of words with the word head in it, like heading, header. Um, and so there's certain words, right, like that are very frequent in English languages, and that when you chop it up, you should actually chop it up in a way that's more efficient, so you can map it to concepts more easily. But when you go to Russian or German or French or Chinese or Japanese, but then changes. And so then if you train on multiple languages, what is the most efficient way to map multiple languages to the same concept? Because obviously a chair, if you have someone that's Russian, Chinese, Japanese, Brazilian, and someone in the US, what a chair is, they can tell what a chair is, even if the languages are different.
What about like languages that use characters for writing? Do they have totally different series of problems, or do they have to think in terms of uh, written get out of the sort of the character language and convert into something like English or Arabic or something like that?
Right. So if we look at Mandarin, for example, it's really a pictographic kind of a language where one character means one word. So we don't, so you say in Chinese and in Mandarin, um, it's actually quite different, because you don't spell out a word like we do in English. It's an actual character. So the character for wood looks a certain way, the character for water looks a certain way, but those words can be used to create new words. In those cases, they're called radicals. So a wood radical can be in other words. right? Like if you're talking about carpentry, there might be a wood radical in the word for carpentry. If you're talking about a forest, well, a forest is made of 2 trees. A jungle is made up of 3 trees. So that wood radical is used multiple times in multiple places to mean different things. And so in those cases, right, you couldn't use the same English tokenization method for Mandarin language because it's just so different.
So how do the Chinese do tokenization?
They actually use more of a byte oriented way because so when we type words on a typewriter or on a keyboard or on a laptop, we spell it out. Similar thing happens with Mandarin, except that you start with a radical. So let's say you want the character for horse. You would start with a radical, and then you would pick the actual character. But in the computer, it uses UTF-8, Unicode standard. And so that has a well-defined byte sequence that tells you what that character is. And so then in cases of like Japanese kanji or Mandarin characters or Korean Han characters or even Hindu or like in Germany, there's a character that's called the S set, which is a double S, right? Which you don't have in English, but if you're in Germany, like that's a super common character. So in those cases, what you have to do is you use the UTF kind of the byte format and use that to map to a token.
Got it. And do English letters or words, parts of words map to bytes as well, or is it doesn't work that way?
So that's one of the challenges, right? With when you're training a language model and you're training it on multiple languages. So for example, when Siri first came out, Siri only supported like English, and it took them months to support other languages, right? Because again, different character sets, different like with Mandarin, the sequence is top down, right to left. With English, it's left to right and top down. So, and books are in the opposite direction. So in Chinese, in Mandarin, the book starts from the backside and flips forward, right? So like, for example, a lot of people that like manga and they order books from Japan and they start with the way that they think it is an American comic book. They're like, why is this backwards? It's like, because it's Japanese.
Yeah.
Flip it over the other way and read it the other direction.
Well, it's surprising to me that people started with any language as opposed to getting away from characters and letters and didn't normalize on something that would be common to all languages, like a concept or something like that. Like the fact that you'd have to do it totally different for a German letter or a Chinese character.
Yeah.
It just seems inefficient and seems like we could have thought about that a little bit differently at the very beginning.
Well, I'm sure that they did, right? But the problem is, if you're English, if you're an American, for example, and you grew up in the US, I mean, what are the chances you know Hindi or Mandarin or German
Yeah,
or
you're not going
Russian?
to know that. Yeah, you go with what you
Right?
know.
Right. So it's just either like start with English because that's my first language. And then I'm just thinking about what's the easiest way. Then later on, if someone says, hey, I live in Russia or I live in Poland and I want you to change your model to support Polish. Okay, so now you can take your approach and see if it works for Polish. Or if someone in Japan says, hey, make it work for Japanese kanji, well, okay, let's try it and see what happens.
Well, do you think LCMs get us? Do you think they advance the AI story here significantly, or is this just going to be a footnote in history?
I think it'll push things forward. The trade-off is a static token mapping approach is much easier to understand because you've defined it. And so it's static. If you want to, so in the case of Anthropic, when they were doing the sparse autoencoders, if you want to know, okay, what happened at layer 40 when the input came in, the prompt came in and it did its thing and multiplied and added, what were the tokens that it spit out and what are the rankings of those tokens? Because you go, okay, token 5 is this, token 6 is that.
Yeah.
And so it's really easy to then analyze from layer 1 to the end exactly how it calculated the probabilities of the inputs and outputs. But now that's dynamic. Well, if I take a version of the model, let's say at the beginning, let's say like iteration 1000, and then it ran for 6 months, we have iteration 1 million. Well, those token mappings are probably going to be different. And so now the problem is exponentially harder because if you want to understand what the model is doing, it's changed over time. And so now, how do you analyze it? Like, it's not static, it's dynamic. So now you got to track every version now between version 1 and your final version and track how it changed in order to understand how did it decide this is the right token mapping? And then how did it weight that token so that it understands the concept of a share?
Wow, seems like it's there's a big trade-off there, sounds like.
Yes, so there's a trade-off in terms of flexibility, because now you don't need to train 6 to 8 months to get a new version of the model. So that's a big win.
Yeah.
Because every time you want to change how granular your model is, you have to like load everything up and run it for 6 months.
Not to
Upgrade
mention, yeah, not to mention the fact that we think in terms of concepts, we don't think in terms of tokens.
Yep,
So
exactly.
it's along the pathway of a human brain a little bit more. Well, this is good. It's a fun one to look at. We'll have to keep an eye on LCMs. We'll include the video. It's a good video. It's only 8 minutes long, and you can watch that. You can also find us on Spotify. So if you don't like this format, you can listen to us in just pure podcast mode. Peter, thanks again, and we will see everyone next time. Thank you.